The positron or antielectron is the antiparticle or the antimatter counterpart of the electron. The positron has an electric charge of +1 e, a spin of a 1/2, and has the same mass as an electron. When a low-energy positron collides with a low-energy electron, annihilation occurs, resulting in the production of 2 or more gamma-ray photons. Positrons may be generated by positron emission radioactive decay, or by pair production from a sufficiently energetic photon. History, theory. In 1928, Paul Dirac published a paper proposing that electrons can have both a positive charge and negative energy. This paper introduced the Dirac equation, a unification of quantum mechanics, special relativity, and the then new concept of electron spin to explain the Zeeman effect. The paper did not explicitly predict a new particle, but did allow for electrons having either positive or negative energy as solutions. The positive energy solution explained experimental results, but Dirac was puzzled by the equally valid negative energy solution that the mathematical model allowed. Quantum mechanics did not allow the negative energy solution to simply be ignored, as classical mechanics often did in such equations. The dual solution implied the possibility of an electron spontaneously jumping between positive and negative energy states. However, no such transition had yet been observed experimentally. He referred to the issues raised by this conflict between theory and observation as difficulties that were unresolved. Dirac wrote a follow-up paper in December 1929 that attempted to explain the unavoidable negative energy solution for the relativistic electron. He argued that an electron with negative energy moves in an external, electromagnetic field as though it carries a positive charge. He further asserted that all of space could be regarded as a sea of negative energy states that were filled, so as to prevent electrons jumping between positive energy states and negative energy states. The paper also explored the possibility of the proton being an island in this sea, and that it might actually be a negative energy electron. Dirac acknowledged that the proton having a much greater mass than the electron was a problem, but expressed hope that a future theory would resolve the issue. Robert Oppenheimer argued strongly against the proton being the negative energy electron solution to Dirac's equation. He asserted that if it were, the hydrogen atom would rapidly self-destruct. Persuaded by Oppenheimer's argument, Dirac published a paper in 1931 that predicted the existence of an as-yet unobserved particle that he called an antielectron that would have the same mass as an electron and that would mutually annihilate upon contact with an electron. Feynman, and earlier Stueckelberg, proposed an interpretation of the positron as an electron moving backward in time, reinterpreting the negative energy solutions of the Dirac equation. Electrons moving backward in time would have a positive electric charge. Wheeler invoked this concept to explain the identical properties shared by all electrons, suggesting that they are all the same electron with a complex, self-intersecting worldline. Nambu later applied it to all production and annihilation of particle-antiparticle pairs, stating that the eventual creation and annihilation of pairs that may occur now and then is no creation or annihilation, but only a change of direction of moving particles, from past to future, or from future to past. The backwards in time point of view is nowadays accepted as completely equivalent to other pictures, but it does not have anything to do with the macroscopic terms cause and effect, which do not appear in a microscopic physical description. Experimental clues and discovery. Dmitry Skobeltsyn first observed the positron in 1929. While using a Wilson cloud chamber to try to detect gamma radiation in cosmic rays, Skobeltsyn detected particles that acted like electrons but curved in the opposite direction in an applied magnetic field. Likewise, in 1929 Chung-Yao Chao, a graduate student at Caltech, noticed some anomalous results that indicated particles behaving like electrons, but with a positive charge, though the results were inconclusive and the phenomenon was not pursued. Carl D. Anderson discovered the positron on August 2, 1932, for which he won the Nobel Prize for Physics in 1936. Anderson did not coin the term positron, but allowed it at the suggestion of the Physical Review journal editor to which he submitted his discovery paper in late 1932. The positron was the first evidence of antimatter and was discovered when Anderson allowed cosmic rays to pass through a cloud chamber and a lead plate. A magnet surrounded this apparatus, causing particles to bend in different directions based on their electric charge. The ion trail left by each positron appeared on the photographic plate with a curvature matching the mass-to-charge ratio of an electron, but in a direction that showed its charge was positive. Anderson wrote in retrospect that the positron could have been discovered earlier based on Chung-Yao Chow's work, if only it had been followed up. For copyright Rick and Irene Joliot-Curie in Paris had evidence of positrons in old photographs when Anderson's results came out, but they had dismissed them as protons. Production. New research has dramatically increased the quantity of positrons that experimentalists can produce. Physicists at the Lawrence Livermore National Laboratory in California have used a short, ultra-intense laser to irradiate a millimeter-thick gold target and produce more than 100 billion positrons. Applications. Certain kinds of particle accelerator experiments involve colliding positrons and electrons at relativistic speeds. The high impact energy and the mutual annihilation of these matter-antimatter opposites create a fountain of diverse subatomic particles. Physicists study the results of these collisions to test theoretical predictions and to search for new kinds of particles. Gamma rays, emitted indirectly by a positron-emitting radionuclide, are detected in positron emission tomography scanners used in hospitals. PET scanners create detailed three-dimensional images of metabolic activity within the human body. An experimental tool called positron annihilation spectroscopy is used in materials research to detect variations in density, defects, displacements, or even voids, within a solid material. See also, beta particle, radioactive decay, list of particles, positron emission tomography, positronium, proton, positronic brain, references, notes. Citations. External links. What is a positron? Website about positrons and antimatter. Positron information search at SLAC. Positron annihilation is a method of experimental physics used in materials research. New production method to produce large quantities of positrons. Website about antimatter. Positron Laboratory, Como, Italy. Website of the Aegis, Antimatter Experiment, Gravity, Interferometry, Spectroscopy, CERN, Synopsis, Tabletop Particle Accelerator. New tabletop method for generating electron-positron streams.